Hello, and welcome to the Neural Designer channel. Today, I will be explaining the mathematics behind artificial intelligence, specifically the learning problem in neural networks. We will study the learning problem in neural networks from the perspective of functional analysis and calculus of variations. First, we will define some mathematical concepts. A function is a binary relation between two sets that associates each element of the first set to exactly one element of the second set. A function space is a non-vector space whose elements are functions. For example, C1, the space of continuously differentiable functions, or P3, the space of all polynomials of order 3. An optimization problem consists of finding a vector that minimizes a function. Find x asterisk such that f is minimum. For example, for the function f equals x squared, the minimum is at x equals 0. A functional is a correspondence that assigns a number to each function belonging to some class. The notation for it is uppercase F. A variational problem consists of finding a function that minimizes a functional. Find y asterisk such that f is minimum. For example, given 2 points, a and b, we consider the functional of length. The function that minimizes the length between the 2 points is a straight line. A neural network is a biologically inspired computational model which consists of a network architecture composed of artificial neurons. Neural networks are used to solve approximation, classification, and forecasting problems. The learning problem in the neural network is the following. This applies to any type of neuron. The neural network defines the function space. Then the loss index formulates the variational problem. Finally, the optimization algorithm solves the reduced function optimization problem. We will explain each of these steps one by one. Let's start with the neural network. A neural network spans a function space, which we will call V. It is the space of all the functions that the neural network can produce. They go from a set X to a set Y. This structure contains a set of parameters, which can be adjusted to perform specific tasks. Each function depends on a vector of 3 parameters, theta. The dimension of V is the number of parameters in the neural network. For example, here we have a neural network. It has a hidden layer with a hyperbolic tangent activation function and an output layer with a linear activation function. The dimension of the function space is 7, the number of parameters in this neural network. The elements of the function space are of the following form. Here we have different examples of elements of the function space. They both have the same structure, but different values for the parameters. Next, we have the loss index. The loss index is a functional that defines the tasks for the neural network and provides the measure of quality. The choice of the functional depends on the application of the neural network. Some examples are the mean squared error or the cross entropy error. In both these cases, we have a dataset with k points, x sub I, y sub I, and we are looking for a function y that will fit them. We formulate the variational problem, which is the learning task of the neural network. We look for the function y asterisk in V, for which the functional f gives a minimum value. In general, we approximate the solution with direct methods. Let's see an example of a variational problem. Consider the function space of the previous neural network. Find the element y asterisk such that the functional of the mean squared error is minimized. We have a series of points and we are looking for a function that will fit them. We have taken a random function y equals minus x for now. The functional is not minimized yet. Next, we will study a method to solve this problem. Finally, there is the optimization algorithm. The objective functional uppercase f has an objective function lowercase f associated. The variational problem is reduced to a function optimization problem. We aim to find the vector of free parameters, theta asterisk, that will make f have its minimal value. With it, the objective functional achieves its minimum. The reduced function optimization problem will be solved by the optimization algorithm. There are many methods for the optimization process, such as the quasi-Newton method or the gradient descent. Let's continue the example from before. We have the same set of points and we are looking for a function that will fit them. We have reduced the problem to function optimization. It is solved by finding the vector theta asterisk that will minimize the function of the mean squared error. This is done with the optimization algorithm. After finding this vector, theta asterisk, we obtain the function y asterisk that minimizes the functional. This is the solution to the problem. In conclusion, we have explained neural networks from the perspective of variational calculus. The neural network spans a parameterized function space. In this space, we formulate the variational problem. We must minimize a functional to solve it. To do so, we reduce it to a function optimization problem. This is solved with an optimization algorithm, and we obtain the function we were looking for. Thank you for watching. Hopefully, this video helped you understand the mathematics behind neural networks. Subscribe to our channel for more content on machine learning.